Hi everyone, and in this lecture we are going to discuss about the polar form of complex numbers at first, and then we are going to discuss the exponential form, and finally we'll see how we can compute the roots of a complex number and how we can deal with the powers of a complex number. So as you can see, I have already written down some things, and the topic is the polar form of the complex numbers. You can see that there is a diagram, and this diagram represents a complex number in the argand plane, or so to say the complex plane. These are also called argand planes, so that's why I have written it like this argand plane thing over here. Now this complex number over here is denoted as z1, and so far we have discussed only the Cartesian representations of complex number, that is including x and y while writing z. Now if you see this graph, you can see that there is this r and there is this theta, there is x and y. So x and y, these are familiar to us, and r is what? R is the distance of this complex number from the origin, and theta is just an angle that the complex numbers makes with the positive real axis, or let's say the real axis itself. Now from this triangle over here, let me just highlight it again, this triangle, you can easily derive the relations that is appearing over here, that is x equals to r cos theta and y is equals to r sin theta. This is basic trigonometry. So this is one way to represent the components of a complex number from Cartesian coordinates to the polar coordinates. That means you are taking x and y's and you are expressing them in terms of r and theta, and if you then use these expressions and put it over here in the z, you should get something like this. That is, this z1 is equals to x1 plus iy1. Then you call this x1 and y1s in terms of r and thetas, you put them in, factor r out, and finally your complex number z is coming in terms of r and theta. Okay, and what is r? Again, r is just this square root over x1 squared plus y1 squared, that is the distance, and theta is just tan inverse y by x. Okay, and now we want to be more precise about this theta thing, because there is no confusion about r, but there is a little bit of confusion about the theta, because you can rotate around this origin and you can always end up on the same point as many times as you want. Let's say you rotate 2 times, 3 times, 4 times, and so on. So that's why instead of using just theta, we are going to use theta is equivalent to theta plus 2 pi n. Now when you do this theta plus 2 pi n thing, there are two things to keep in mind. One thing is that these two thetas are actually not the same thing. So if you call this theta and call this theta prime, this theta prime would be actually the principal argument that we emphasized in the previous lecture. Okay, and also note that this 2 pi n can be visualized in terms of this cosines and sines as well, because sines and cosines are periodic functions and they have this period over, let's say theta goes to theta plus 2 pi n, where n belongs to z. Now after this, you write this complex number in the polar form, this r times cosine theta plus I sine theta, and then I have written another line over here. So let me just indicate the transition. This is our polar form that we initially got from the upper calculations, but then I'm transitioning to another form, that is z is equals to r exponential to the power I times theta. So where is this coming from? This is pretty easy to see if you just write down the series expansion, or so to say the Taylor series expansion for the exponential function that is given over here. You expand out the terms and then you should get two separate series. So one series would be something like this, and then there would be another series like this, and this would be the series of the cosine theta, and this would be a series of the sine theta. This is pretty easy to do, you can check it out yourself. And why this expression is far convenient than this one is because when you want to compute the powers of complex numbers, so let's say you have this z2 and you want to compute z square. In the Cartesian format it's pretty easy, but if you want to compute something like z to the power 1000, this is not easy in the Cartesian format. So that's why you use these exponential representations, because if you use the exponential representations like here in the second line, you can see that this power would just distribute itself to these two objects, that is r2 and e to the power I theta, and you can easily compute them. So it is as simple as that. And if you take a numerical example, you can always go back to this 3 plus 5i. You can compute the r2, the radius or the distance, whatever you want to call it, the modulus, and this would be just square root over 34 to the power 1000, whatever that is, and it would be e to the power I theta, and theta is what? Theta is tan inverse 5 by 3, whatever that is. You get some numerical value using the calculator, and then you just multiply it by 1000. That's it. It's as simple as that. And from these experiences we can derive another powerful theorem, and that is called the de Moivre's theorem. If you check that z to the power n is actually r e to the power I theta to the power n, and then you distribute the power among r and e to the power I theta, from there you can see that z to the power n would actually be r to the power n times cosine n theta plus I sine n theta. What have I done here is that I am writing this theta n as theta prime, and finally when I'm done using the identity e to the power I theta is equals to cosine theta plus I sine theta, I'm putting back the values for theta prime. And in fact this e to the power I theta is equals to cosine theta plus I sine theta. This is a famous identity, also known as Euler's identity. And from this thing you can see another thing, that is the de Moivre's theorem, that you have this e to the power I theta to the power n. You can write it as e to the power I theta n, right? This is valid. But e to the power I theta is equals to cosine theta plus I sine theta, right? So you just put this identity and you get this cosine theta plus I sine theta to the power n. But on the right hand side you have e to the power I theta n, and again you can imagine theta n as theta prime, just what I did over here. And e to the power I theta n is what again? Cosine n theta plus I sine n theta, and this is the de Moivre's theorem. You can even derive many kind of trigonometric identities using this relation. So you don't have to expand, like let's say there is a problem that tells you to compute this thing 10,000, right? So you can just write this like this. This is the power of the de Moivre's theorem. You don't have to expand this huge number in terms of the binomial transformation, binomial expansion and all that. So now we want to clarify more about our theta, because our argument that we discussed earlier in the previous lecture, you saw that we gave special emphasis on the principal argument. So we want to do things in terms of principal argument because it's well defined, it's a well defined thing, right? And to do that, first we need an identity, that is e to the power 2 pi I is equals to 1. And when you write a complex number, you can write it as r e to the power I theta, but here I have written e to the power I theta and then I have added a multiplicity, that is a 2 pi n. Why? Because again, if you have a complex number over here, you make some rotations. Let's say you're rotating for the first time, you obviously end up back here, and this is a rotation of 2 pi, right? And let's say then you decide to rotate again. So now you have rotated 4 pi, that means 2 times. So each time you rotate the rotate about the origin, you pick up a factor of 2 pi. So that's why there is this 2 pi n, or so to say the multiplicity, and this theta is now the principal argument. So now this form is actually more well defined, and this is the representation for a complex number in the polar coordinates. And this form enables us to compute the roots of a complex number as well, as you will see over here. So you are asking a question whether you can compute a certain quantity that is a root of a complex number. So z is a complex number and you want to compute the nth root of z. You want to compute this. So let's say you have some w, another complex number. So w belongs to c, and you are saying that w is equals to the square the nth root of z. So our goal is to compute the w. Now in the next step, that is over here, I have stepped up both of these sides into the power n. That means I have just did this. I did this on both sides. I raised the power to n. And since w is a complex number as well, we are writing w as capital R e to the power I theta, and we are doing z as small r e to the power I phi, where phi is the principal argument, and then there is this 2 pi m, where m is 0, plus minus 1, plus minus 2, etc. Now you have an expression in terms of r and thetas and phi's on both sides. Now how do we solve this? To solve this, we need some more ingredient that I didn't discuss earlier. That is, if you have two complex numbers z1 and z2, when these two complex numbers are equal, so if you consider the Cartesian form x1 plus I y1 and you write z2 as x2 plus I y2, they were only equal if and only if x1 equals to x2 and y1 equals to y2. That means two complex numbers are only equal to each other if the real parts and the imaginary parts of those numbers are separately equal to each other. How this comes? One way to see it is to just pull back this x2 and y2 on the left hand side, and you will see that you have another complex number in the form that tells you that there is this x1 minus x2 plus I y1 minus y2 is equals to 0. And this is only possible if both of these components, that means x1 minus x2 and y1 minus y2, are 0 separately. Otherwise it's not. You can easily see it from the graph that if you just take x1 minus x2 equals to 0, and if you take y1 minus y2 not 0, you would still get an imaginary number, which is also a complex number with a real part being 0. That's why both of them have to be 0 simultaneously, right? So this is the Cartesian case. What about the polar case? That's easy to do as well. If you just take z1 as e to the r e to the power I theta 1, and note that I'm not writing the multiplicity right now, you can assume that the multiplicity, that is the 2 pi n thing, got absorbed in this theta. Okay, so you write these two in polar forms, you get this r1 cos theta 1 plus I r1 sin theta 1. Similarly for z2 you get this expression, and you are saying, okay, I'm demanding these two to be equal. If I do that, then again by this argument, similarly the real parts and the imaginary parts have to be equal to each other. That means the real part of z1 and the real part of z2 should be equal to each other, and the imaginary part of z2 and the imaginary part of z1 should be equal to each other. That gives us these two expressions, and now you can divide these two expressions and see that this is just saying to you that theta 1 should be equals to theta 2, and if you use this in any of these expressions, you will get a r1 equals to r2. So in the polar form, two complex numbers are equal if the radius, you can call it a radius or modulus, whatever you want to call it, if these r's, that means r1 and r2, they are equal to each other, and the theta 1 and theta 2, they are equal to each other. That's the only way two complex numbers in the polar representation can be equal to each other as well. In fact, you can also show that these two implies each other as well. That means the conditions that makes the polar complex numbers equal on the Cartesian representations are the same conditions that make the complex numbers to equal to each other in the polar representations. This is also easy to show, but we are not going to show that here. So using these two things, we can write that capital R to the power n should be equals to small r, and theta should be equals to this guy, right? This is just simple algebra. Now, since w was what? W was r e to the power I theta, right? We have found r, we have found theta, and hence we have calculated the roots. But there is a little subtlety. That is, n is a fixed thing. N is already given in your question, or n is something you already know. What about m? That can go from 0, plus minus 1, plus minus 2, and so on. Is there a restriction? The answer is yes. You can only go up to n minus 1. If you go beyond that, then what happens is that you get the same root again and again. This is again easy to show. If you just put m equals to n, there would be a factor of 2 pi. So theta would pick up a factor of 2 pi. There is a I in front, and e to the power 2 pi I is just 1. And a geometric way to see this would be, let's say you have a equation that says that x cube equals to minus 1, and you should get 3 roots. That is the fundamental theorem of algebra as well, and we'll try to prove it in later lectures, that if you have a polynomial of n degree, there should be n distinct roots. Okay, so now this x cube equals to minus 1 should yield 3 roots, and in the Argand plane or the complex plane you can show these roots like this. And if this root comes from m equals to 0, and this comes from m equals to 1, and this comes from m equals to 2, and then if you take m equals to 3, you will see that you are again back in this m equals to 0 point. And if you put m equals to 4, you will be over here. If you put m equals to 5, you will be over here. So it's like going through the same points again and again. So that's why there is a restriction that it should only go up to n minus till n minus 1. And this is how you can calculate roots of complex numbers as well. So this will be it for today, and I'll see you guys on the next lecture. Thank you.